Okay, folks, we can get going. Any questions from anyone about anything? We've been going through your lab reports. We're almost through them. We're going to aim to have those returned to you in the next day or two so that you have comments to look at for the next one. Overall, they look pretty good, but we'll get those returned as soon as we can. Any questions about any of that stuff? I'll just remind you that we're back to sort of our normal due dates with Lab 2. So that is to say, everyone's lab report will be due before the start of your lab section next week. Okay. Any concerns from anyone? My plan for today, given that we are now on week 3 of Lab 2, that means that starting really this afternoon, many folks will start working on Lab 3 because people will finish their Lab 2 week 3 checkoffs starting today, and so they'll start working on Lab 3 today. So we really should start talking about Lab 3 here pretty soon, but I thought it might be worthwhile to take one lecture and wrap up every loose end associated with Lab 2, give everyone an opportunity to ask any pending questions about optimizations and so forth, and essentially take as much time as we need to wrap everything up with Lab 2, and then with remaining time, I'll introduce Lab 3 and maybe tease some of the interesting content associated with it, though I expect that probably we'll mostly get into that on Wednesday. I'd like to spend today just really talking about Lab 2 and optimization options. So I'll just remind you that at this point, now that you've all finished the week 2 checkout, really the primary goal for Lab 2 this week is optimization. You've got at least 10 balls falling through your Galton board at this point, and among a small number of other little bells and whistles, you've really got most of the bells and whistles already implemented as a part of last week's checkoff. Your primary goal this week is just to try to get as many balls as you possibly can. And so I'd like to spend today talking through at least a handful of strategies that might help with that, and hopefully to have a conversation about it to the extent that some other folks have come up with some interesting ideas that might help with optimizations. So, does that sound reasonable to everyone? And let me just say too, I had a couple of groups that they got, maybe 50 balls falling through the Galton board last week and said, hey, we'd like to check off for Lab 3. Don't do that yet. The whole fun or for week 3 rather, the whole fun of this lab and really most of the pedagogical point of this lab is this week. The whole hope is that you're going to spend this week trying to get as many balls as you can. A good goal, I would say, would be maybe 2,000-ish. Try to get about 2,000 balls. How many do folks have at the moment? Did I hear 200? 200? That's a good starting point. Aiden? 4,000? That's great. 300? Okay. Okay. So if you're going into this week at, maybe high tens to low hundreds of balls, that's a great place to be at this point. And now this week, try to bring it up to 1,500, 2,000-ish. And as you make each of these optimizations, make a quick note, right? So that, okay, we made this change to our code, and now we can get this many balls at 30 frames per second. We made this change, now we can get this many balls at 30 frames per second. That's a great table or a great plot in a lab report, okay? And it's interesting to actually measure how much time each of these optimizations gets you back. But let's talk through a few of these. And I thought that the way we would talk through this is by taking a look at the pseudocode. And as I mentioned when we first talked about this pseudocode, there are many opportunities in here to optimize and to speed things up. And I want to just point to a few of them. So what this pseudocode shows you is a nested for loop. And so what this is saying is in your animation thread, do the following for each frame. And it's saying for each frame, go through every ball, and for every ball, go through every peg, check if you're colliding with that peg, and if so, do the collision physics associated with that peg. So the first thing that we might consider optimizing is you could ask yourself, does every ball really need to look at every peg? And in the event that the pegs were moving around so that their positions were changing from frame to frame to frame, then yes, it's not obvious how you would optimize that away. But in our case, if we consider this sort of screenshot here, all of the peg positions are fixed. which means if you know your ball's Y position, you don't need to check a whole bunch of rows of this Galton board because you know, just given your Y position, the pegs, say your Y position is down at like, 275 or something, you're near the bottom of the screen. Just based on that information alone, you know, and you need to go search through the first few rows of that Galton board, right? And so you might consider giving some thought to how you might optimize this step here. Given that for each ball that you're going through, you have easy, immediate access to that ball's X and Y position on the screen, does having that information and also knowing the static positions of all the pegs in the Galton board, does that give you the opportunity to save yourself some search? I think that it probably does. And then as we go through here, okay, let's suppose we're looking at some ball, and for that ball, we're considering a candidate peg with which we might be colliding. I want to point out both sources of optimizations and sources of bugs that I've seen, just in case you're still seeing this as well. You'll notice that when we're considering a particular peg for collision, the first thing that we do is get the difference in X position between our ball and the peg and the difference in Y position between our ball and the peg. And before we do anything else, we first ask the question, is the difference in X position less than the sum of the radii of the ball and peg, and also is the difference in Y position less than the sum of the radii of the ball and peg? And only that being the case do we then carry on and figure out the actual root sum of square distance separating these two and check for collisions and so forth. I want to just remind you, some folks have seen that and deliberately or accidentally left this check out. If you leave this check out, it can lead to some bugs with some very strange symptoms. And the reason for that, I'll just remind you, is all of our arithmetic here is in fixed point. This, by the way, if this is not the case for your animation loop, this is a definite optimization that you want to implement this week. There should be precisely 0 fixed point arithmetic going on at all in your animation loop. It should, did I say fixed point? Floating point. There should be 0 floating point arithmetic going on in your animation loop at all. It should all be fixed point. But this means we have to be a little bit careful because we're working in fixed point. What we have to be careful about is we have to keep in mind that the particular fixed point range and resolution that you're probably using, unless you've changed it, which we could talk about, this is possibly another optimization, but unless you've changed it, you're probably using 16.15 fixed point. So that means you have 16 integer bits, 15 fractional bits, which means the biggest number that you can store is something like, 32,000 or so, right? So if we don't do this check, the first thing that happens after this check is we compute the root sum of squares distance that separates our ball from the peg that we're considering. If you don't first check that your difference in X position and Y position is less than some reasonable threshold, and you then go and do these squares, the consequence could be, if your ball is very separated from the peg that you're considering, that you overflow your fixed point data type in those squares. So let's say your ball is separated in the X dimension by 400 pixels or something. You hit dx squared there and you square 400 and you end up with a very large number, bigger than you can contain in your chosen range and resolution for fixed point. The consequence of that is, C doesn't mind that you've overflowed. It's just that the output of that square ends up looking like a small number instead of a very, very big number. And you might observe that your ball collides off of nothing or moves in some strange way because it thinks it's very near to a peg that it is in fact very separated from. And so if you're seeing weird bugs like this, another symptom of this bug could be that your peg is inexplicably just skipping through rows of your Galton board or just missing pegs. If you're seeing that kind of symptom, double check that you are in fact doing this check. The other reason to have this check is this is relatively quick for us to just verify, and in the event that that condition is not satisfied, then we needn't do all of this relatively expensive arithmetic, right? We just throw that peg out right away. We know we don't have to check for collisions with it. Okay, but in the event that that this condition is satisfied, then the next thing that we have to do is compute the root sum of squared distance between us and the peg. And as implemented in this pseudocode, that distance is being computed as the square root of dx squared plus dy squared. And in some of your animation loops, I suspect that right now it may be the case that you're computing this by doing fix to float, square rooting it, and then doing float to fix of that square root, right? Where you're doing a little bit of a dance where you're converting back to floating point to do the square root and then perhaps converting back to fix. That dance is very expensive. And so you want to get rid of that, but it raises a question of, well, this is an expensive operation. How exactly do we do this without doing something floating point? And I alluded to a solution to this in a previous lecture, but given that we're now in the optimization week, I thought I would just point you directly to one solution. There's a link up here to a Wikipedia article on an algorithm called the alpha max plus beta min algorithm. Some of you have already implemented this, but others of you have not. And so in the event that you haven't, I just want to draw your attention to this. If we click at this, this is a great trick to know. This is an algorithm that allows for us to very inexpensively approximate the root sum of squares of two numbers. It's not perfect, but we're not going for perfection here. We're not trying to build a very, very high fidelity physics simulation. What we're trying to build is a computer graphics demonstration of correct looking physics, right? So our goal is really that this looks right. And in order for it to look right, we can be a little bit sloppy with our calculation of some of these things. And so what this algorithm says is, instead of computing the square root of the sum of squares of a squared plus b squared, as shown up here, what we could do instead is first ask the question, which is bigger, a or b? Which is the bigger magnitude number? This is the one slight gotcha here. We're comparing absolute values for these two values that we want to approximate the root sum of square of. So you ask, which has the bigger absolute value, a or b? So in the event that a is -3 and b is 2, the answer would be a with a larger maximum value or absolute value of 3. And then if we want to compute the root sum of squares of those two numbers, we can approximate this as some parameter alpha times the maximum of those two absolute values, a and b, plus some other parameter beta times the minimum of those two. So we ask which is bigger, and then we approximate root sum of squares with that algorithm. And what this table shows us is, for different choices of parameter alpha and parameter beta, how good is that approximation? And you can see that, you know, it could be as good as a largest error of 6% and a mean error of about 3%. That's a pretty darn good approximation. Better, in fact, than we probably need for our purposes. And so you could look at this and, boy, line 2 here looks pretty darn attractive. Line 2, with an alpha value of 1 and a beta value of 1/4, you can see that we get a mean error of 3.2% between our approximation of the root sum of squares and the actual value of the root sum of squares. And in the worst condition, we get an error of a little over 11%, a little over 11.5%. That's pretty good. And furthermore, alpha is just 1. We don't even have to do anything there. No multiply, no nothing. And beta is a power of 2. So that, too, does not require any kind of multiply. That's just a shift right by 2. And so we can replace this very expensive root sum of squares operation, in which you might presently be doing fix to float sort of tricks. You replace this whole thing with a comparison of absolute values, which, by the way, you've already got absolute values up here, right? You needed them for that if condition. So you've already got them. You don't need to go re-get them. You figure out which one's bigger, and then your distance here becomes a add and a shift. That's going to get you back a fair number of balls, for certain. Okay. And then we can continue to go through here, and we're going to look for other opportunities to speed things up. Let's see. Well, one opportunity to speed things up, it's not precisely inside of this, but it has to do with the whole exercise here, when you start getting into the optimization, is you want to take as much out of your animation loop as you possibly can. So you ask yourself, what is it that I am absolutely required to do and required to redraw every frame, and only do those things every frame, and do those things as quickly as you possibly can. So one of the things that you have to do every frame is erase and redraw every ball. So one question that you might ask is, well, if I, right now, just because it's the way that the example code did it, many of you might be drawing your balls using the fill circle routine that is a part of the VGA driver, or library rather, which is okay, but if we take a look at, let's take a look at fill circle here. Fill circle helper, draw round rect. If we take a look at it, it calls this fill circle helper routine. Draw circle helper, where's fill circle helper? Here it is. And so every time you call fill circle and you pass in some parameters x and y for the center of the circle and a desired radius, what fill circle will do is figure out algorithmically, based on your specified center of the circle and your desired radius of the circle, which pixels should it turn on. And so by calling fill circle, it doesn't know before you call, but right before it goes through all this arithmetic, you call fill circle. It doesn't know for that specific position on the screen and desired radius which pixels it needs to turn on. It will go through and figure it out every time. And all that I'm drawing your attention to is that that's kind of expensive. It takes quite a bit of work, actually, for the CPU to figure out which pixels it should turn on for a circle at a particular place on the screen of a desired radius. And so one easy optimization is you say, well, I don't need for it to figure out which pixels to draw every time. What I could do instead is I'm going to design my own circle, right? I'm going to bitmap my circle so that I can make my own little VGA function where I pass in an x and a y coordinate, perhaps holding the radius fixed to some nice value. And you will have bitmapped this in the sense that when you pass it the x and y coordinate, it just knows which other pixels it needs to turn on around that center coordinate. It doesn't need to go figure it out every time. That's going to speed things up considerably. And you could do that not only for the balls falling through the Galton board, but also for the pegs that compose the Galton board. Those two, you needn't call fill circle every time and actually figure out which pixels should be redrawn if instead you figure it out on your own, bitmap it, and then just tell it, here are the pixels that you should turn on given a center coordinate. Yes?
So when you say bitmap, does that mean we should have like some, we should store like the pixels that we need to turn on?
Yes.
And then we just, oh, these are the pixels to turn on.
Just turn them on. Yep. 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 And it needn't figure it out. And this is making an assumption that the size of the pegs on the Galton board aren't changing. By the way, you could implement it such that they change. You would just need a few different bitmaps for different size, Galton board pegs, and likewise for the balls.
But for the balls, those just change every iteration. So don't we have to update that bit mask like every iteration of the loop because it's different every time?
They're changing position but not shape. And so you would parametrize this such that if you specify where you would like the center for your ball to be, it's parameterized such that it just knows, okay, based on this center, I turn on this one, this one, this one. Yeah. Another thing you could do, even simpler, is you could say, well, if you stand 2 feet back from the screen, little squares look an awful lot like little circles. And so you could say, I'm not going to draw my balls falling through the Galton board as circles. What I'm going to do instead is draw them as little squares. The most extreme version of this would be a single pixel, right? You could make the balls falling through your Galton board a single pixel. I encourage you to do that to see how many you get. A single pixel is a little bit hard to see, but a 2 by 2 square, so 2 pixels on each side square, that's very visible, looks an awful lot like a ball, and it is radically less expensive to draw and redraw than a circle using this fill circle routine. By the way, speaking of redrawing, if it's the case that right now every frame you are redrawing every peg in your Galton board, it's perfectly okay. I mean, so many of you have made the observation that after a collision, it's very often the case that a ball will slide a little bit into the peg, right? Because it's moving at some number of pixels per frame, slides into the peg, and then when it leaves, there's a big gap in that peg that you do have to fix. One way to fix that is every frame, redraw all the pegs. Another option would be every frame, only redraw the pegs with which you have actually collided to reduce the number of peg redraws that you have to do. Now, if you start to get up to the 1,000, 2,000, 4,000 number of balls, it may be the case that you're colliding with most pegs every frame, but I'll bet not all pegs. Even with 2,000 or so, 2,000 to 4,000 balls, it is pretty darn rare that you're going to hit these outer pegs with the parameters set to their default values. You could adjust the parameters such that that becomes much more common. But with the parameters set to their default values, it's pretty darn rare that you hit the pegs out here in the outer corners. Okay? And so you could think carefully about, is there a way to only redraw the pegs that I have to draw? Yes?
So one optimization I did was like the text that is like labeling the value that I'm drawing. I don't redraw that every frame, I only redraw the value. But like if I make the bounciness really high, then they'll just go all over the screen, and then they'll erase over that.
Right.
So what I did is I just said, okay, if I just cap the bounciness to a specific level such that they don't go up the top corners, then it's fine. Is that like an okay assumption to make?
That's fine.
Okay.
That's fine. Yeah. There, you should be able to vary. What does the specification actually call for? I think what the specification actually calls for is that you need to be able to adjust the number of balls falling through the Galton board. And 5730 students need to be able to adjust one of the other parameters by way of the potentiometer. Could be bounciness, could be one of the other ones. But I make no specification as to the range over which you have to actually vary these things. It has to be enough that it's observable, right? So we can actually confirm that it's doing something. But yeah, you may clamp that to some reasonable value if you choose to. But you do bring up another good point about optimization, which is, like I said, the thing that you want to be thinking about is what is the bare minimum stuff that I absolutely must be doing every frame, and I only want to do that stuff every frame. Everything else I will do less frequently. So you mentioned writing text to the screen, right? One of the requirements is that on the VGA screen, you need to display the number of balls being animated, the total number of balls that have fallen through the board since reset, and the time since boot. Now you might make the observation, we're putting this stuff on the screen to be read by human beings. How quickly can you as a human being actually read changing numbers on a screen? Does anybody know how many independent events people can generally detect per second? I think it's as low as 5. I'm not, maybe it depends a little bit on the experiment. In any case, it's small, right? And so the observation here is just that. Let's say you're reporting time since boot. Do you need to redraw this time every microsecond? Most certainly not, because those lower n number of digits are just going to be a blur of completely indecipherable text. So instead, rewrite the time once a second. So it's just counting 1, 2, 3, 4, and only redraw that specific number one time per second, not once per frame. There's a question in the chat. Let me just see. Yes, yes, yes. Thank you, Bruce. So there's a few optimizations to speak to with the text. One is you only rewrite the text that has actually changed. And so let's suppose, for instance, you have on display the current number of balls that are being animated. That is to say, let's say at the moment there are 100 balls falling through the Galton board. And so you would have some text there saying like active balls, 100. You don't need to rewrite active balls, 100 30 times a second. You only actually need to rewrite it when the user changes the number of balls that are falling through the Galton board by adjusting the potentiometer. And furthermore, when you do actually rewrite the text to the screen, a very expensive way to do that would be to draw a big old rectangle over all of the old text, and then rewrite the text where you drew the rectangle. A more efficient way to do this is you only rewrite the characters that have changed. So if you have some string of text, colon, and a number, you don't rewrite the text. You only rewrite the number characters at the end that have actually changed. You could do that by drawing a black rectangle just over those numbers. I'll also just draw your attention to, and hopefully some of you have discovered this, if you go to the VGA graphics library, there are routines here that allow for you to set the text color. There's also this set text color to function, which takes as arguments not just the color of the text that you want to write, but also a background color. And so it will automatically erase the background behind a character before it redraws it. Now, some of you may have used this and may have noticed a slightly sneaky bug, which is, let's say you have 100 balls falling through your Galton board, so you have like number of balls, 100, and then you turn it down to 50. Some of you may have observed that now that there's one less character, the character that used to be there doesn't actually get erased, right? Unless you went through and redrew it. A slightly cheesy but very effective solution to this is when you do the sprintf to the character buffer that you're going to put to the screen, put a couple of spaces after the number, right? And as many as the maximum number of digits that you would ever expect to be written to the screen. You're probably not going to have 5 digits of balls on the screen. I'll be incredibly impressed if anybody gets over 10,000 balls. I think that sounds really hard. I'm not exactly sure that's possible. So you know, if you have 3 spaces after the number, you can guarantee that it's going to clear all the digits, right? Yes.
So I know there's 2 functions. There's write string and write character. I think. Is there a way to write character?
I think there's just write string.
Okay, never mind.
Yeah.
So anyway, for write string, is the best way to go about creating that string, because obviously you can't pass in a literal for it because it's a character array. Is the most efficient option to use printf?
Yes.
Okay.
And in contrast to printf, which communicates data to a serial terminal over a UART port, sprintf is just shoving data into a character buffer. So that doesn't have the same time penalty that you would associate with a printf. Yeah. Yeah. Okay, yes.
I don't know if the function that is the branches to draw character, but we were kind of like experimenting with doing draw character versus write string, like drawing character individually.
Okay. I'm not sure. Let's see. So you're using a collection of these draw cars? Is that what you're saying?
And like for the number, we were saying having 4 digits, we could just draw like 0, 0, 0 for 58.
Sure. You know, it would be interesting to measure. I don't have a good intuition as to how much time that might save you, but it could save you some, certainly. Any other questions about these sorts of things? Okay, so another source of optimization here. Remember, we're trying to be very conscious of what are the time-sensitive processes that we absolutely must execute 30 times a second. What are the time-insensitive processes that we needn't? So we mentioned that one of the time-insensitive processes is the writing of this text. Another time-insensitive process is this histogram at the bottom. Do we need to redraw this histogram 30 times a second? Well, again, this is for human beings to look at. And so probably not. Probably we don't have to redraw this histogram 30 times a second. You might instead keep track of, the number of balls in each bin over some number of frames and update the histogram at a slightly lower rate than you're updating the ball positions. And furthermore, much like the text, when you redraw this histogram, if you put a big black rectangle over this whole bottom of the screen and then redraw all of the rectangles that compose the histogram, that is going to take, comparatively speaking, a very, very long time. You're adjusting a ton of pixels there, right? Every pixel that you adjust requires that you go to a particular place in an array, rewrite its value. And so you can imagine that's hundreds and hundreds and hundreds of adjustments. And furthermore, if you do that, you might see an interesting artifact, which is that your histogram will sort of blink in and out. It kind of flashes in a strange way. The reason for that flashing is that the update rate of the VGA screen is 60 or 70 hertz, something like that. But it's asynchronous with when we're actually updating the histograms, erasing and redrawing the histograms. Right? We are not being careful, for instance, to only adjust the histograms when the VGA is in blanking. We could be adjusting this when the VGA is in active mode, right? So we're actually, it's rastering through and we're changing pixels as it's doing so. The consequence of that is you see flashing that represents the frequency with which you're updating the histogram beating against the frequency with which the VGA screen is updating. There's two processes occurring at slightly different rates and they sort of beat against one another. Ends up looking like flashing. So instead, when you're drawing these histograms, you're going to end up with a bunch of rectangles here that are growing and shrinking as the balls fall through the Galton board, right? They're kind of, some get taller, and as they more fall through, they'll level out ultimately to something that probably looks like a Gaussian, depending how you have the parameters set. But all these rectangles are growing and they're shrinking a little bit. Instead of adjusting the height of a bin of your histogram by erasing that whole rectangle and redrawing the rectangle at a new height, a more efficient way to go through this is to maintain a little bit of extra state, where every bin in your histogram remembers what its previous height was, right? So you have an array there of length 17 or something that is the current height of each histogram. As balls fall through, perhaps in the next time you update the histogram, you want to draw that bin at a new height. Well, if the histogram bin grows, rather than erasing the whole rectangle and redrawing it, what you could do instead is draw a little rectangle on top of the old one that grows it a little bit. Right? So you're only adjusting a very, very small number of pixels to adjust its height just a little bit. If the histogram needs to shrink, if that bin needs to shrink, then you draw a black rectangle on top of the existing green rectangle, or whatever color you've chosen, to shrink that histogram bin a little bit, so that we're only adjusting the minimum pixels that we actually need to adjust. Furthermore, there is no explicit requirement that your histogram bins be filled rectangles. They could just be the outlines of rectangles. It carries the same information. It's really just a matter of aesthetics. And it saves you a bunch of pixel adjustments if instead of filling every rectangle with just a whole bunch of green, just draw the outline of a rectangle and adjust their heights. Any questions about that? So how frequently could you get away with updating the histogram? Once per second is probably a little bit slow. But, I don't know, maybe 5 times a second? Update your balls at 30 frames a second, but I bet you could get away with updating your histogram at maybe 5, and it would look just as reactive to a human observer as it did at 30, in all likelihood. How are people doing with the potentiometer? Good, good. Any noise issues? Yeah? Okay. Question or noise issue?
Kind of both.
Kind of both?
Yeah.
Okay. Do you want to ask the question?
Yeah, so I was finding the noise was definitely kind of an issue.
Mm-hmm.
I guess one thing I tried was like, setting a threshold value for the noise where if it goes above a certain threshold, that's when it's actually detected as like I'm changing the potentiometer. I don't know if that's a good way to go about that.
That seems like a reasonable solution. It sounds to me like you're sort of describing a hysteresis. Yeah. And that was going to be one of my suggestions, is you could consider doing something like that. The other thing that I'll just mention is the most straightforward way to use the potentiometer to adjust the number of balls would be to do something like sample the voltage with the ADC. You get a number, right? If you're using all 12 bits of the ADC, you'll get a number between 0 and 4096. If you shift out the lower 4, based on the observation that your effective number of bits is only 8.7, so there's a lot of noise down there, then you're going to get a number between 0 and 256. One way that you could use that number is just to use it to set the number of balls, so that as you turn the potentiometer, you are directly using the potentiometer to set the number of balls. An alternative way that you could use it is that as the user adjusts the potentiometer up so that the voltage that you're reading is increasing, you're using the rate of change in order to adjust the number of balls up. And as you detect the voltage going down, you use the rate of change of it to adjust the balls down. In other words, you're not directly using the ADC output to set the number of balls, but instead looking at the changes in ADC output to adjust the existing number of balls up and down. This has a secondary advantage for the 5730 students that will be required to adjust at least 2 parameters by way of the potentiometer. That let's say you adjust, let's say you're using the ADC to directly set the number of balls. So you go to the balls setting and you adjust it up to, well, I don't know, 150 or something. And then you click the button that allows for you to adjust gravity or whatever parameter you've chosen. And you turn the potentiometer in order to adjust that. If you're not careful, let's say you want to go back and adjust the number of balls again, but now your potentiometer is in a new position because you were using it to adjust a new parameter. You click back to the number of balls and it just slams back to wherever the potentiometer happens to be located. If instead you're looking at changes in the ADC output to adjust the number of balls, you mitigate that problem, right? Because you don't actually care about the absolute position. You care instead about the changes in the output from frame to frame to frame, or from ADC read to ADC read. Question?
If you do it that way, wouldn't you end up in the range values that would be accessible with that potentiometer actually changing?
Yeah, so you may end up in a situation, and in fact, I think you can observe this in this demo video. That was the strategy that I used. But you're correct that you could turn this thing up all the way, and then you run out of room to turn the potentiometer. And so what you end up having to do is click out of the adjusting state, turn it down, click back into the adjusting state, and then you can continue to crank it up. So it's both. You could think about this both as an advantage or a disadvantage. It's kind of both. The advantage is you have an insensitivity to the absolute location of the potentiometer, and furthermore, you run out of range. But you also run out of range if you're directly using the ADC to set the number of balls. The advantage of the second option is you can always turn it back down and then keep going up indefinitely. Yeah. You will the specification does ask for you to indicate when you have missed frame rate, and the easiest way to indicate that is, let's just go to, for instance, the animation demo here. Right? Each of your animation thread, the way that you are enforcing a 30 frame per second update rate is you grab the time at the beginning of animation. Here is where you're erasing and redrawing and doing collisions with all of your balls with pegs and so forth. After having done all of that, you figure out, okay, how much time did I spend doing that? You subtract that from your frame rate, and you yield for the amount of remaining time. If this number, spare time, ever goes negative, that means you've taken too much time that frame. You have exceeded your frame rate requirement. And so the easiest way to check and report whether you have failed to meet timing is put a little condition at the bottom of your animation loop that says, if spare time is less than 0, turn on the LED. And then it'll just be very clear whether or not you're hitting timing. And then the game will be, you turn up the number of balls until the LED is on, and then you turn it back down until you find the number at which you're consistently meeting the timing deadline. So it allows for you to sort of experimentally find where that number is for you. There are some no-brainer optimizations that we talked a little bit about last time. One is overclocking. Don't forget to do that. You just get twice as many balls basically for free. Okay, so you can adjust the clock rate of the processor from 125 up to 250 megahertz. You could experiment with going even higher. I make no guarantees. Just remember that every time you adjust that, you also have to adjust the clock dividers in your VGA state machines. But we talked through how to do that. But doubling the clock rate just gets you twice as many cycles every frame. You also, of course, have 2 cores. And so this will be the week where you'll be encouraged to, in the event that you are doing all of your ball animation on core 0 at the moment, which would be the wise choice at this point in the project. At this point, what you're going to want to do is make a second version of your animation thread, put it on the other core, and have both cores working on animation simultaneously. Now, this is parallelizable in a rather straightforward way because we aren't doing ball-ball collisions, right? Every ball only collides with the pegs, and so you can give core 0 a whole bunch of balls to collide with pegs. You can give core 1 a bunch of different balls to collide with pegs. Those balls on the 2 cores don't have to know about each other. They'll pass right through one another. And so it is a straightforward parallelization. Yeah?
Is the best way to read the ADC value with the DMA channels done? Because what I have right now is I'm just using ADC read on core 1 and then just updating those accordingly.
So you could set up a DMA channel to read the ADC. I think probably using ADC, how to put this? I don't think you'd get a tremendous return on that. You might get some speed up, but I don't think it would be tremendously much in this lab because you could make the observation that it's a human being adjusting the potentiometer. You needn't read it any faster than a few times a second, probably. And each call to that ADC read gathers one ADC sample, which will take, every time you read the ADC, it takes 2 microseconds. 96 cycles of the 48 megahertz clock, 2 microseconds. So using ADC read would be perfectly fine, I think, in this case. Though it would be interesting to experiment if you've got the time and inclination to trying to use a DMA channel there.
So just using ADC read every tick of the while loop?
Well, every tick of a while loop. You probably don't have to read the ADC 30 times a second. You could maybe read it at the same rate that you are, for instance, drawing the histogram. Okay. Any other questions about this? So okay, another just no-brainer. I know that this is an obvious one, but it's really easy to overlook. Don't have any print statements in your animation loop. It's perfectly fine to have them in there when you're debugging, but it can be an easy thing to then overlook. And you're going, why am I only getting 15 balls or something like that? You take out the print statement and all of a sudden you have like 500. Okay? Remember, the print statements are really expensive for reasons that we talked about in a previous lecture. Those are going through a UART channel. The baud rate's only 115200, 10 bit times per character. And so you very rapidly kill your timing just with a single print statement. So no floating point at all in your animation loop. No print statements, of course, in your animation loop. Avoid so no floating point suggests no floating point square roots. So use alpha max beta min to get rid of that floating point square root to compute the root sum of squares. Be thoughtful about drawing. Make the observation that fill circle is a very expensive routine, comparatively speaking. So represent your balls in a way that is more efficient to draw and redraw, either by way of a bitmap or by replacing them with 4 pixels. I would encourage you to experiment with 1 pixel, see how many you get. I think you'll be surprised how much speed up you get just by dropping your balls from some number of pixels to 1. Be thoughtful about which processes need to occur at which rates. Your time-sensitive process is your ball physics updates. 30 frames per second requirement. You have to erase, recompute, and redraw every ball 30 times a second. The other processes that are going on here, be thoughtful about how frequently they actually have to occur. How frequently do you actually have to rewrite stuff to the screen? How frequently do you actually have to draw the histogram? And then when you do rewrite those things, only touch the pixels that you have to touch. If you don't need to erase a whole bin of a histogram, don't. Just erase the top little bit. Just add to it a little bit. If you don't need to fill the whole rectangle with colored pixels, don't. Just draw the outline. Overclock. Get you twice as many cycles. Put the balls on 2 cores. That'll probably get you pretty much twice as many balls falling through the Galton board. Only redraw the pegs that actually have been collided with and are required to be redrawn. That'll get you back some time. What else? And you could give some thought as to whether you actually need to check every peg for every ball. You know where the balls are. You know where the pegs are. The pegs don't move. So can you eliminate some subset of the pegs for a particular ball given knowledge of its Y position, for instance? Can you just know, based on its Y position, that you don't need to go check these rows of the Galton board? That there's only maybe 2 or 3 rows that you actually have to check? Yeah.
Just a quick question. When writing the balls on 2 different cores, is there any issue with memory consistency between them?
That's a great question. So do we need to worry about conflict or race conditions or anything between the 2 cores if we've got both cores animating their own subset of the balls on each core? So what is the shared resource between them? The only shared resource, I believe, if we assume that only one of the 2 cores will be, for instance, redrawing the pegs, right? Because you don't need both doing that. Both will be writing to the VGA pixel array. And so it raises the question, what happens if both core 0 and core 1 try to write to the same pixel at the same time? Now, I need to double check this, but I believe it's the case. I need to recheck the data sheet, but I believe it's the case that if both cores truly try to access the same place in memory at the same cycle, I think core 0 takes priority, if I recall correctly. You don't need both cores drawing the histogram. You do need to take into account the balls on both cores, but so that suggests to me that, let's say core 0 is drawing the histogram. Core 1 would be writing to some variables that would be observable to core 0 to update the histogram, but core 0 wouldn't be required to write those variables also. Core 1 would be writing it, core 0 would be reading it. Yeah. Yep. Yep.
Is there an appreciable difference in performance between like a dual core reader-writer system rather than both being writers as well?
Let me see if I'm understanding properly. Like, are you proposing, is there an advantage to having only one core, for instance, update the histogram as opposed to having both cores contribute to updating the histogram?
Yeah, for example, so that's an example where one core is constantly updating like the histogram array, and the other core is only reading them, rather than them both editing the same histogram array.
In terms of time savings, I need to think about that, but it certainly seems to me that it simplifies accessing shared resources. I think. And like I've said previously, you could give this some thought. You can't do anything wrong. It's just that things that you do have consequences. And so you could ask yourself, let's suppose that, for instance, I don't protect pixel memory, and I allow for both cores to just read from it and write to it. What could be the consequence of me doing that? And am I okay with that consequence given my goals? And as long as you can articulate, here's what I'm doing, here's what the potential consequence of that is, and here's why that's okay given the specifications of the lab, it's perfectly okay. Yeah? That's right. That's right. Okay, so we're out of time for today. I hope that you will really enjoy this particular week of this lab. This is the week that makes this whole lab fun. This is the get obsessive about trying to save cycles part of this lab, which tends to be a blast. So in any case, I'll be there this afternoon. I'll see many of you then, see the rest of you on Wednesday.